Hi, my name is John, and I'm here today to talk about wind and what causes it. There are three different things that cause wind. The first thing is the Earth's gravitational field. The second thing is extraneous gravitational fields from the Moon, Jupiter, other planets in our solar system, the Sun, and possibly even other star systems that surround us. The third thing that causes wind to move is temperature. uh, Energy from the sun heating up certain parts of the atmosphere. Now, I want to impart the most important thing that you can do to help yourself understand the nature of the atmosphere that surrounds the Earth is to think of the atmosphere as a solid mass, just like water, as though it were water, as though we are fish living in a water atmosphere because there are just as many atoms. The atoms are just as thick in the atmosphere around the Earth as it is in the Earth or in water. We just can't see them. Gases are invisible mostly to our eyes, so our human brains get tricked into thinking that there's nothing there. I look out the window at my neighbor's house across the street and I can clearly see it. There's electromagnetic waves bouncing off of it into my eyeballs in the visible light spectrum, and there's nothing blocking my vision of that house. If there were a solid mass there, I wouldn't be able to see it. Like if there was a hill between us, it'd be solid mass. I can't see through a hill, but I can see through gases. And I just want to impart the most important thing about understanding the atmosphere or becoming an atmospheric expert or genius or scholar or engineer is to think of the atmosphere as a solid mass. And remember, the plane's wing cutting through the air gives it lift depending on the rudder controls and the lift and the dive controls, the same as a submarine. Okay, so think of the atmosphere as a solid mass, just like water is a solid mass. And then you'll understand that atoms are thick in the atmosphere and can move. They're fluid, just like water is fluid. They can move. The first thing that I mentioned was Earth gravity. The Earth has its own gravity. It's very important to sustain life on Earth because the gravity that's within the Earth is what keeps the atmosphere within our atmosphere. It keeps the gases in our atmosphere. Without those gases, we wouldn't be able to live. We'd have nothing to block super harmful radiation from the sun or other sources, and we would have no oxygen to breathe. So those were the necessary things for humans to evolve or be created by God in order to live on the surface of the earth. We can live because there's gases in our atmosphere. So they are atoms, just like any other atoms. You can pick up a can of soda, and that can of soda is made of atoms. You pick it up and move it. Gases are the same thing. I've got a handful of it right now. See it in my hand? So you have to think of atmosphere as atoms, just like any other mass, because it is. And the second, so when I say that the Earth's gravity, why that's important to the movement of wind and or water, the two are inexplicably tied together as both fluid. Getting some weird messages on my computer here. Water and atmospheric gases are pretty much the same thing. They react pretty much the same way under the same set of circumstances and changing circumstances. So, but the Earth's gravity is constantly pulling on the atmosphere and the water, anything fluid above the surface of the Earth, and even the crust of the Earth. It's pulling heavier things down toward the bottom, and the lighter things are up on the top because that's how gravity works. It works on atomic weight. That's why heavy things are drawn into the soil. I know that sounds crazy, but trust me, gravity is that strong. So the Earth's gravity is constantly pulling down on the atmosphere and the oceans. It wants to keep that atmosphere right there. It's fighting to keep that atmosphere right where it's at. We call that stasis or static. The Earth is fighting to keep that plane of atmosphere right where it is, and the next plane, and the next plane, and the next plane, all the way around 360 degrees, constantly trying to keep it from moving. Now come extraneous forces, like the moon that comes along. And we know that the moon has gravity. That's an extraneous gravitational force coming across the Earth, which is spinning. And as the moon goes across, it's attracting little particles of atmosphere. Okay, so what force is fighting that? It's the Earth's gravity. It's trying to keep those from moving. So the moon by itself really doesn't have a great effect on atmosphere. And more so on water, because water is a little bit heavier to the Earth's gravity. But in the atmosphere, you usually have more things than just that. And water too. And that force is temperature. That was the third thing we mentioned. Temperature is very important in the movement of gases. Now, what does temperature do? Increased temperature is going to take a ball of air. Let's just say we have a ball of air like this, and the sun is directly overhead beating down on this ball of air. And we know that those are atoms in there. So they are being struck by the energy of the sun. They are heating up. They are getting warm. And even though they're invisible, and we think they're not there, there's a bunch of atoms between my hands right now getting hit by the sun, and they are warming up. What happens when atoms warm up? Well, their bonds break more easily. Their little electrons start moving a lot faster. Okay? Let's jump back to the water example in the ocean for right now, and tides, because that will help us further understand the atmosphere. So the moon comes across east to west, and it's coming over here, and it's pulling that water over here. And as it goes further, it's pulling that water up, and when it gets all the way to the other shore over here, the high tide is on this side now. Okay? So then the moon goes around the back of the Earth. The tide, ocean tide, kind of undulates a little bit until it becomes static. The Earth's gravity is keeping it in place. It's fighting that extraneous gravity to keep the water where it is. But lo and behold, here comes that moon again. Bah, here comes the moon, and it goes all the way over here, and now high tide here again. Undulation a little bit, okay. Static. We got stasis here with this level, pretty level ocean. Oh, here comes that old moon again. Ah, man. Okay, here comes the moon, and it goes over here. Now we got high tide over here again. Undulation, and it repeats over and over and over. Let's take a side trip just for a minute. Where do we get all those little choppy white cap waves all throughout the ocean as the ocean is undulating back and forth with the gravity of the moon, or without the gravity of the moon as it settles down to stasis? Those choppy forces are a high pressure water. The moon's causing a high pressure here in this water. If it's in conjunction with the sun, depending on where the sun is at, relative to where the moon is at. And the sun, remember, the sun is also pulling the water. Secondarily, the sun is heating the water in certain spots. So the sun is leading the water, or leading the moon, so to speak. If we view the Earth as relatively not revolving, but just stasis, it would look as though the sun were leading the moon. The sun would be over here, the moon would be back here. The sun is heating this water over here, and although the moon is attracting this water, making a high pressure, this heated water, electrons are going like this, and this water over here, high pressure, even though it's cooler, it's going to crash into this faster moving water. And when two things crash into each other, we've got energy. Imagine two cars going along and they hit head on, each one doing 50 miles an hour. Well, they don't just stop here. That energy has to go somewhere. Well, it crumples up the front, pushes the engine into the passenger compartment, it all crumples up. Where does that energy go? It goes down in a car because of the Earth's gravity. Two vehicles hit head on, that goes down. If you look at any spot where an accident has occurred recently, you'll see where that bad accident happened, the cars went down, they dig out actual chunks of the pavement where their suspensions went down and hit the pavement. There will be holes in the pavement where that car did that. Now, whitecaps, water, the cold, high pressure water pulled by the moon hitting a warmer temperature water, which was heated by the sun, remember, causes many things to happen. If this were cold temperatures and this were just slightly colder temperature, it would look about like this. And what would happen when those two forces meet? They would go up because the pressure of the water would push them up. So contrary to the two metal vehicles going down with the pressure, two whitecaps go up. And here you got a whitecap right here. And you got these little whitecaps happening all over the moving ocean. Okay. Now it gets really bad when the sun is intensely hot. The water is near to the equator. The moon is nearer to the equator because you've got a greater pressure here. And if Jupiter gets into the mix, which has another high value of gravitational pull, you could end up with a very bad situation with very much hotter water here than you got coming from the moon here. And when they crash, this one's moving, the electrons are moving so fast that it causes a swirling effect. And that's when we get into hurricanes and twisters, tornadoes. But those are more like perfect storms, and there has to be a lot of different things, a lot of different heated and cooled areas coming together to cause that to happen. And they have to be symmetrical for that swirling to start taking place. And kind of, if you could look at it either way, water or atmosphere acts the same way. Atmosphere gases, when they warm up, they actually become even easier to break. Water molecules are easy to break. You can pour water in your hand and just watch it break right out and flow through your fingers because that's the bonds breaking, the very simple bonds of the hydrogen and oxygen. But the molecules in air break even easier than that when they're heated. So when you have heated air and it's being pulled by gravitational forces into cooler air, where does that energy go? It usually ends up becoming a vortex. Okay. Not all vortexes are dangerous. You know, you've seen little dirt devils. I don't know if you've ever been down to Texas or anywhere in the deserts of the United States, but you'll see little dirt devils, what they call. They'll be tiny little tornado things just crop up anywhere, and they're not dangerous, but that's the effect of warm air crashing with cold air. It usually will cause a vortex, especially, like I said, when the circumstances are such that the cold and the warm areas are convoluted in such a way that will help to make a vortex. So it's a little bit longer than I wanted to go. I hope I explained everything here in the 10-cent tour of understanding the atmosphere and how wind is created. If not, let me know, and I'll write out a script for. This is unscripted. I'm just kind of going off the top of my head here. But if it's difficult to understand, I hope you'll let me know, and I'll be glad to script out a video that makes it a little bit easier. This is not a paid channel, so I don't have funds to make a lot of fancy graphics like others. I'm just a guy, and I like science, and I like expressing scientific thoughts, and this is how I do it. So anyway, I'm John. Thanks again. I'm out. Have a great day.